Good. Welcome, friends and students. In this video, I'm gonna talk to you about. I'm gonna expand on the video that I made about planar lamina moment and center of mass. So let's write down what we're gonna talk about. So in the first video that I made, I didn't expand too much. So I thought when I explained it to my brother, I wanted to tell him a little things that I found, and he told and he noted, and I asked him a question and he answered me, and I thought maybe I should tell you guys too, because I wanted to expand a little more as well. Okay, so if you remember on the first video, we talk about the mass of the planar lamina. So the planar lamina, we were talking about an irregular shape lamina. So let's say this is your x-axis, this is your y-axis, and then you have your lamina here that goes from x equals a to x equals b. And I told you guys that to find these formulas for center of mass and moment, I had to partition the lamina into rectangles, and I told you that this width has to be delta x, and of course you need to find the height. Okay, so now where did I come from those formulas? Well, we first said that the mass is equal to density times area. That's one of the first things I told you. And then density, we call it rho, and then the area, we said that was the height, which is f of x minus g of x, and then that we multiply times delta x. So that gives the mass. And as we know, the moment is equal to the center of mass. The formula is equal to total moment divided by mass. So here we have the mass, but we need the moment, the total moment. So how do we do the total moment? The total moment, okay, first we found in the previous video, we found the moment about the origin. The moment about the origin is from here to here for that little rectangle. So, and we said that that moment is equal to the mass, this mass here, times the height. The height from here, not the height, times the distance from here to here. And we call it, I don't want to call it height, so we're gonna call it distance. But in the previous video, I didn't tell you where did that term that I use, the term that I told you about to finding the center. I gave you this one, f of x plus g of x divided by 2. But I didn't tell you where this came from. So in this, but I told my brother, and he actually gave me a good explanation for that actually. So, and I wanted to talk, like by expanding, I also wanted to tell you about that one, because how would you find the distance from here to here? First, we're finding the middle point here, the middle point of the rectangle, because that's what we need to do for this particular concept. So the way my brother told me is, well, let's find the midpoint. Okay, so that was the midpoint. We go from here to here. What is that distance? If this is g of x and this is f of x, that distance from here to here is what? G of x and then we do plus to find the distance from here to here. How would I find the distance from here to here? We do f of x minus g of x divided by 2. But this, looking at this, it has nothing to do with what I gave you for the distance before. But if you simplify this as follows, you put everything divided by 2. Because this is a 2, I have to put a 2 here. But because I put a 2 here, I have to multiply the top by 2. So the top becomes 2 g of x plus f of x minus g of x. Now by canceling this and this, I get the formula that I gave you. G of x plus f of x divided by 2. So I didn't show you this before, but this is the way we derive this distance from here to here, to the center of the rectangle. So basically the moment is this whole thing here. The moment of the little rectangle is gonna be m times f of x plus g of x over 2. That makes more sense. And now now x bar, which is the center of mass, is easy. I just have to do the total moment divided by the mass. We have the mass and we have the little rectangle. So how will I find the total moment? I need to, because we partition this, I need to find the sum of all this area, of all these moments. So that requires a Riemann sum. So we go from I equals 1 to n of m, the mass, and of course the mass we have to put I, because if for each little rectangle, and then we do f xi plus g xi over 2. But remember, this is an approximation. If we want an exact answer, we need to take the limit. Okay, so now we take the limit of this sum. So this is the total moment. So the total moment, we take the limit as delta x, each little delta x approaches 0, or as n approaches infinity of this one here, of the sum. By doing this limit, we call the fundamental theorem calculus, and we convert this sum, this limit, into a integral. So by fundamental theorem of calculus, this limit becomes m, the total moment of the whole lamina, becomes a to b of the mass times f of x plus g of x over 2 dx. So this becomes this. This is an approximation, this is an exact answer. Okay, and now the final step is just remember, let me write it down. So the mass is equal to, Of course, we can do the same similar procedure of this, and then we can say that the mass is equal to A to B of rho. We pull out the rho time, which is density, times the area. What's the area? It's gonna be it's gonna be f of x minus g of x dx. And then and now that we have the formula for the total area of the lamina, for the mass and for the moment, all we need to do is divide this. Okay, so x bar is equal to total moment, which is this here, over the mass. And as we know, the mass here is gonna be equal to rho times the area, which is f of x minus g of x. No, actually, I'm sorry, that yeah, that's the mass, yes. Okay, so now that's all I needed to do. Now you plug in these integrals here, you should get your final formula. So thank you very much. Don't forget to subscribe, please.